Good morning, everyone. Thank you for attending our first seminar for the AnalytiXIN Manufacturing Data Asset Research Project, which is handled jointly by 3 universities, Indiana University, Purdue University, and University of Notre Dame. Today is our first open seminar, and we are very fortunate to have Dr. Ming present her work on HVAC data that she has analyzed using this manufacturing data assets approach. So Dr. Q, I will just turn this over to you. Thank you again for agreeing to hold our first seminar for us.
Okay, thank you, Ellen. Okay, I will take the sharing my screen. Here. Can you see my screen here?
Yes.
Okay. So, hello everyone. Thank you for attending this seminar. First, let me introduce myself. My name is Ming. I'm from Architecture Engineering in Lines School of Civil Engineering at Purdue. I'm a full professor here, have been in Purdue for 12 years. So my research area is not in the statistics or science or computer science, but in the energy, building energy and the building system energy analysis. So I work on the building design, performance analysis, operation control, and building simulation toward to sustainable built environment. So I'm very honored to work as a member in the Purdue team for this manufacturing facility energy optimization project. Today I'm going to present some my insights in terms of the energy audit and my first initial investigation to this demonstrate building EMC score. Let me just get started with the first overview of the energy situation in terms of the manufacturing in the United States. So as we can see at the left side, this is coming from the Energy Information Administration of United States, EIA data. So from 2002 to 2018, manufacturing facility consumed almost 30 quadri BTU, as you can see, 20 to 30 quadri BTU, which is about 30% of the total United States energy consumption. Total energy consumption in the United States is 100 quadri BTU. So as you can see, it's a very important component in our national energy consumption. At the right side, you can see this is about where can we really save energy through the manufacturing facility. This is also done by the EIA. So they did the survey across the United States on all the manufacturing facilities. So what you can see up here, almost 20 to 30% of the manufacturing facility actually carried out the energy audit over here on the top. And that's the data in 2018. Okay, so the percentage of the, if we zoom in to look at the energy audit, what are the aspects or measures the manufacturing facility taking to improve their energy efficiency? So the first top, what you can see is the lighting system. The second one is heating, ventilation, air conditioning systems. So obviously this one, I roughly calculated the percentage is about 16 to 20% of the overall whole establishment in the United States. So that means 20 to 20% of the manufacturing facility select the retrofit or energy improvement on the building heating, ventilation, air conditioning system. So that's also, I guess, is aligned with the AWS energy optimization vision. So the vision for this Insight project, I guess, is really trying to taking use of HVAC system as a start aspect, right, to optimize the manufacture facility. So our vision here in AWS energy optimization to save is to save 10% of energy consumptions. Let me see, next one. So it's not just EIA data, also collect some data from the reference. This is from a paper published by the group of Klazak in 2013. So I guess this is trying to give you more insights of what are the actual measures they did for energy saving by retrofit HVAC system. What you can see the most of measures around efficiency motor, right? And install the piping insulation and the smart control, and etc. So potentially from this paper, the most of implementation is around those measures. At least 14% of the implementation is around those measures. So based upon the data we have and also the platform AWS already established, our Purdue team proposes to use Internet of Things science and based sensing system and cloud-based data collection through the machine learning and artificial intelligence to reduce building energy usage. Our goal is to save 25% of the energy consumed by building HVAC system. So the detail 3 aspects we're gonna carry out through this research is first is the IoT and cloud-based data collection and computing. And we will, second aspect, we will generate a model based upon machine learning and AI. The model is for the building the energy consumptions and also fault detect and identification of the energy conservation measures. So the last one is actually we're gonna generate a platform so the manufacturing industry companies can get on the platform so the system can provide service, provide analysis, and propose conservation measures. So that's basically our goal and proposed concept. Next one, I'm going to talk about the energy audit process we are involved through the process. The first one is actually a walkthrough site visit of the facility. So this is a traditional method. The reason we still take this because we want to have a physical sense and really link the data with a physical system. So we focus on the visual inspection and looking into the historic energy usage data. And the facility so far we have is EMC score. It's a new facility, but we started to collect more and more data. So this later in this presentation, I will talk about my visit, the walkthrough site visit. Then the second process is step is the on-site measurements and data collection. So I guess we're gonna have a little bit of measurements because I still see some data are not collected, especially for energy simulation or energy. Critical energy related parameters are not collected. So we're gonna later on require to install some other sensors here. The last one is the building energy performance analytics. So here we break down to three steps. The first one, we're going to generate the consumption prediction model. Then this model will continue expand for fault detection and diagnostic. Then the last one is based upon the previous two models, we gonna generate, identify the conservation measures. So I will talk about the next one in this this AWS Insight project. We're gonna break down the measurement and data into the three three scopes, three catalogs, categories, right? So the first one is about building, second is HVAC system, and last one is the environmental. So all those data we're gonna need collect at least one complete year, and the data sampling frequency at least 1 hour. Current AWS data actually is pretty good. They have a second, the sampling data is in the second. So for the first category, the building energy usage data. So we're gonna look into the usage of the electricity and the fuel. I haven't seen the fuel data yet, but we have a lot of data in the smart meter on this electricity. The second part is kind of so break down the major end uses. Here we're talking about how much electricity is actually used for building, lighting, artificial lighting system, plug loads, and also for the machines and the HVAC systems devices. Right, so this is really breakdown and use data. So this first category is around the building itself. So it's matter the environmental condition. So what kind of a weather outside it is. So we're gonna collect also the weather data to really develop the building model. The second category is I would say is like narrowed down to components. Here, the building energy system component, heating, ventilation, air conditioning system. So here we focus on the air handling units and the primary loop energy resources device. Here involves the chiller to provide the chilled water, and the boiler provides the heating water for the air handling units. So as you can imagine, the air handling units involves air, involves water, hot water, chilled water. So we're gonna collect all the status of those mediums. So the supply air, return air, outdoor air conditions, and temperature, humidity, and the water flow rate and temperatures, we're gonna collect all of them. Fortunately, we have all of those data available in current facility, demonstrated facility, EMC score already have all of those data. They are available. And the last one is actually related to the indoor and outdoor environment. So the outdoor environment is very close related to energy, building energy usage. So as you can imagine, the basic temperature, airflow, and humidity, and the CO2 level. For the indoor, this is really matter to the human or workers' working environment, and also sometimes related to safety. So we want to also have some observation on the quality of the air and the pollutants level, like a CO2 or some other particles in the indoor facility. So, but our primary for this energy audit is focused on the number 1 and 2. Outdoor environmental data is necessary for the category number 1. Then I'm going to talk about building performance analytics. So in the analytics work, we're going to break down into 4 areas. The first one, we call it energy profiling. So after we collect the data of the building, so the data, we're gonna generate the building total energy usage and end use energy usage profile. So it's on the daily base, weekly base, monthly base, and annual data. So then once we have this energy profile filing, then we can compare to the energy profile, collected by some agency like a EIA, like an ASHRAE, so it's called a benchmark energy profile. So we can compare, see if the studied facility is above average or below or higher. So we can, propose to kind of evaluate where the current, the building energy usage stand in terms of the benchmark. So that's the second one, energy benchmarking. So this benchmarking, we're gonna collect all the data from different resources. The third one is energy consumption calculation and prediction. That's the mainly modeling work. So we're gonna develop the model on both building itself and HVAC system. So, because this is really strongly related to energy auditing and conservation measures. So we're gonna predict the building, the thermal load, which related to the heating and the cooling load of the HVAC system. And once we have this state model, then we will be able to detect the faults and carry out the energy diagnostic. So we will dive into the system, the detailed parameters and the component operation to generate later on generate the energy saving potential measures. So then I will talk more about the energy analytic method here, focus on the model prediction models here. So typical energy audits have 3 methods, right? Here I kind of give you a review, literature review here. So the most traditional way is the first method is engineering method. We use the physical facility parameters, use the thermodynamic heat transfer principles to build the energy model. So we can calculate the building thermodynamics and energy behavior for overall system and also the subcomponent systems. So this kind of model is very elaborate, comprehensive, and accurate. However, it's pretty time-consuming, and it's lack of flexibility to use for other similar facilities. And it requires a lot of input information, very detailed data collection are required. So the second method is actually based on the statistics. So it's a statistical model. So it's taking use of a simply correlationship between the building energy consumption and the key parameters, influencing parameters. Mainly method is the regression models. So there are 2 methods. One is auto-regressive model with extra inputs. Another is the auto-regressive integrated moving average method. So those method is relatively easy to implement. However, the accuracy and flexibility are not so satisfied because the model is strongly related to the data that collected. So then the last method is recent 2 decades scientists and researchers are using, which is artificial intelligence model. So this model is gives a prediction based upon large data. So for instance, like a manufacturing facility, let's say the starch manufacturing facility, the data based upon hundreds, thousands of similar facility data, then use artificial neural network to generate a correlation, then predict the building energy consumptions. So this model is robust and highly accurate and very flexible. So, but it requires a lot of historic data. But I do think AWS platform is perfect fit for this model, because our data is going to be collected more and more and across the United States. And this interesting part of this model is it can be continuous tuning and self-learning and become more accurate and flexible. So that's why our team is going to use this last method. However, we still have the physical model because we know the details relationship of parameters. So our engineering science and the physical model will provide the domain knowledge to guide this artificial intelligence model for this energy analytics in order to optimize optimize the facility for the AWS Energy Insights project. So here is just some proof proposed method we're gonna use for this AI model. So for the first prediction model, we're gonna use a support vector regression after we collect the data. Later on, once we have more and more data, we're gonna use a parallel implementation as a support vector machines to analyze data. And through this model, we use a neural network to detect the faults, right? And also build the correlationship of the key influencing parameters so we can do sensitive analysis. And also based upon this, we can further generate the conservation measures to propose for the manufacturing facility. And the next 2 slides is about our initial thoughts of the needs. This already in the red that means already met, so we already have them. So again, this is kind of the repeating from the data collection slides, but I just want to give you a very short impression here. We collect the data. We need the data for outdoor conditions, right? And parameter listed here, and also for building HVAC system is here. I just skip this details here because I'm going to talk about this later. And some ideas of the conservation measures. We're gonna take a close look at the motors, the insulation, and some dynamic operation, and etc. So in the front, this basically is our kind of roadmap for energy audit of this AWS Insight project. I'm not sure if I pause here or I continue to answer some questions, or I continue to talk about the recent work in the past 2 months. We have proof visit for our prototyping building the EMC square visits and some initial data collection. Valent, should I continue?
Does anyone have any questions? Looks like no, so you can just probably continue. Thank you.
Okay. So in June, I actually went to Indianapolis to visit this EMC Square facility. Had a walkthrough site visit. So this facility is a one-floor building. So it has has 4 building spaces. I guess the front 1/3 of the facility is office building. Then there are 3 big spaces dedicated for GE 3D printing and lighting company and the collaborative workshop. So for the air handling unit, there are 5 identical units served for different spaces, at least here. So air handling unit 1, like in this picture showing here, so serving for the office space, and 2 and 3 for the 2 facilities, and 4 and 5 for the workshop. So this is the GE 3D printing facility. So this is the air handling unit. You can see this is a big printer. I think it just shipped over to the space. They're going to install it very soon. Then this is the lighting facility. So we haven't seen the device and all the equipment moved in yet, but so far this is a large clean space and served by this air handling unit 3. So I did collect all the sensing of this air handling units and controllers. And this is the last one. It's a very large open plan area. So it's supposed shared spaces shared by many companies, so they can work together, collaborate together. So this is the autonomy racing car from one company. So they demonstrated over here. And inside the same facility, they have the air handling unit 4 and 5 to serve in this area. So the air duct are still not installed yet, still in the process of installation. Then, so for the data side, our team, also Purdue team, started to explore the data already uploaded in the AWS bucket as S3. So as all of you already received, so under this bucket we have 2 folders. For the first one is the metal data in the JSON file. So basically I call it like a dictionary. So it provides all the assets and the parameters for each of the assets. And the second folder is the actual data. So it's in the Pocket files. So the data is 1 hour data. It's the values of all the parameters of all the selected assets. So it's not all the assets listed in this metadata are actually uploaded in the S3 yet. So our initial data exploration, we have from a JSON file, we found there are 32 assets. List over here, including 5 air handling units and 1 hot water and 1 hot water system. So this is this is related to HVAC system device. They are also electricity meter data. So here's like a facility. The customer group is means the office. So they have several meters actually as assets collect the data. So at least here's 32 of them. And because I work on the HVAC, so I collect the parameters, actual sensors installed in the air handling unit. So there are 35 of them. Some of them are information type, some of them are status, some of them are the actual operating parameters. So in the red, all those are the parameters we're gonna use for our machine learning. As you can see, it's related to the air and the conditions of air and the water, hot water, and the cold water, chilled water. And this is the hot water system and the boiler. So this is a serving for domestic hot water, like a washing, wash hands or bathroom. And also it's served for the HVAC system. So again, the red one are the parameters we're going to use for our model. So this is a picture that I took on site. They are boilers, basically very beautiful devices here, as you can see. And in the center, that's the control panel. And this is our initial exploration on the AWS, the actual packet files. We summarize this rather than 35, because in the dictionary we have 32 of the assets. So we found that there are only 19 assets data available because the system is still in the developing phase, installation phase. So we will have more data. So far for HVAC system, we haven't seen the data yet. But I think it's a very nice platform. We are already able to download the data and analysis data. So this is just a kind of the showing we visualize the data of the power usage for this. I think this is the center of the power meters. This facility or the device, I don't know where is it, because during the visit, I didn't see this facility. But anyways, just trying to see we are able to visualize the data to retrieve and showing data. This is the temperature for a CNC machine. That's pretty much what I have today. Yeah, so I guess I'm just opening to the questions, right?
If I could ask a question, this is Ali Shakuri.
Yes, Ali, yeah.
Thanks for a very nice presentation. I have a question. You mentioned for the energy analytics, you plan to use the support vector machine, which makes sense. But I was wondering, what was the rationale for the fault detection? You mentioned you're going to use recursive deterministic perception. Are there similar cases in HVAC that this technique has been used, and why you think it's more applicable here?
Yeah, so these methods has been successfully used by Lawrence Berkeley Lab, and also a researcher. I think back to 2015, they published several papers on that. So that focus on both building and building HVAC system. So the fault detect, I guess, is more focus on the cycle and the interaction between buildings rather than compressed or detailed valves, stuff like that. I guess for this project, we will stay at the system and also overall air handling units working principle rather than mechanic device. So sure, the method has been proven successfully used, right, and presented in the paper already. Yeah.
Thank you.
Yeah, thank you, Ali.
Hi, this is Pratik Sharma from Indiana University. Thank you for your talk.
Yeah.
I had a brief question about the last slide that you showed, the temperature graph. That seemed to be sort of all over the place from 20 to 120 Fahrenheit. Do you have any thoughts on why that is so spiky? Is there perhaps some sensor issue or some
No, yeah. So this is the CNC temperature machine. I guess it is a machine operation temperature for supply to the machine. This is not related to HVAC at all. As I mentioned here in the front, right? The uploaded data I download because RT uploaded the recent data in May, the week before, last Wednesday. So last Wednesday, I tried last night. There was a asset or was not in the dictionary. I need to talk to her for the details. But anyway, so we don't have HVAC or hot water or other detailed data yet. So this is just to say we already able to look into the detail of the data, look at the trend worth the time, right? This is just to say, so the platform is ready. As long as we got data, we can go ahead and move on for our energy modeling and prediction. Yeah, this one I guess I don't quite sure this temperature really used for. Yeah.
I see. Okay, thank you.
Yep.
Hi, this is Ariful Azad from Indiana University. Thanks for nice presentation. So you mentioned about some engineering models.
Yep.
That are physically verifiable. I'm just wondering, can you give us some references? Can we use those models to validate the machine learning model in some sense? What do you think about that?
Yeah, so that's also what I'm going to do. The first step, I'm going to work on the relatively simple model. So we call the RC model. This is somehow like an electrical engineer. So we treat the building like the thermal network, like a electrical network, right? So we have resistance and capacitance, right? So we're gonna have our resistance capacitance for the building wall, and maybe I guess the window. I don't see many of windows. So if we don't have window, that's very simple. We just use a simple 1R 1C. Then we have air inside of air. Then we can have a thermal network to build the state space model. Is quite simple. Definitely, if you are interested, I can forward you some reference, and also we have published a paper on those, right? So, but I would not encourage you on use more detailed, comprehensive model, right? So you have to figure out the geometry of the wall, the roof shape, the color, the material. So I guess I would stay at the more abstract, simplified model and use the data to train and tune the model better. Yeah.
Okay, thank you. I can send you an email. I mean, we often debate about interpretability of machine learning models, and sometimes having some physical model would be helpful.
That's no problem. Okay. Yes,
Okay,
send me
thanks.
an email. Yeah.
A quick question. This is Professor Alam from Purdue. One way to make this type of RC model or simple thermal circuit model is to just map the outside with a thermal camera.
Yeah.
And thereby just see the output radiation and just think about it as a composite volume. It's like a cube. And the integral of the surface emission and the power that you're putting in, they must be in balance. And that would allow an experimentally verifiable model, RC model, that although it's simple, but there is an underpinning of experimental validation built in.
Yes. Yes. So basically, we can use some other statistic method to make this model more accurate. So which is used in model predict control. We can use common filters. So we have actual measure data to make our RC model more accurate. And also some uncertainty of the model and the measurement uncertainty can be both considered in this estimator, or we call it a tunable model. So I'm not sure if I answer your question. That's still in the physical models, but highly simplified with a common filter, some method. Right, adaptive common filter to make it better, more accurate.
Thank you. I think the starting simple and gradually building in complexity is the right way to go.
That's right.
To start complex, then it is just too many unknown parameters. Then this is as bad as or as good as machine learning. That in either case you really understand what's going on.
Yes, exactly. Yes. Yes, that's also we often used for energy system, right? So because the building energy system need to interact with the building itself, so the building model must be part of the control. So quite often we need to simplify the building model so we can implement this online smart control for device. So yeah, exactly. So we definitely would not go to much more comprehensive physical model. Yeah.
Hi, this is Jim Wittendorf at Notre Dame. I'm wondering if you are planning on engaging in the utility groups within each of the universities for potential systems or data that they've already got accessible to either add to or help corroborate the data that you plan on getting from new equipment that's installed. The question comes to mind because Daryl Peterson and I just recently toured our Notre Dame's utilities group, and it looks like they've got a lot of that sort of capability now of collecting data and looking at it on a building per building basis. So just wondering if you're leveraging those resources.
Yeah, definitely. I think it's a very good question, right? So I'm just thinking because typical building energy system still use the legacy control system on prototyping. Protocol is the BACnet protocol, rather than like a IoT based sensing. So the integration, I think, is a big part. When I did the tour, I noticed the integration for the team on I-12. It's really it's time consuming and a lot of need dig into it. So collaboration with the facility and also the engineers working in the actual facility is important. However, the whole project, I guess the vision is trying to establish the platform. So how can we develop a platform can really incorporate all those key design or engineers in the platform? I think is very good question, and how can we incorporate later on make the the awareness of the dynamic of actual system is critical. I guess the answer is sure. I need to think further on that. But I think definitely so. It's an important aspect we need to consider incorporating into the platform.
Hello, Ming, Daryl Peterson, Notre Dame. How are you? Thank you.
I'm fine. Yeah.
I had one question, and I know a lot of companies probably aren't going to share their production volumes, but I believe energy consumption per unit is something that they'll understand and be more willing to work on. Because if you come to me and say, hey, Daryl, your electricity doubled in December, January, and February, and I'm making lawnmowers, I'll say, well, of course it did. I doubled my output for the spring selling season. So if we could think, and this is for everyone on the phone, I think, as a per unit, my experience has been manufacturers tend to react to a per unit basis. So if you go all the way back to like slide 2 and you were given some of those energy consumption data as a macro, I mean, do we divide it by GDP? I don't know. It's just, they tend to think more on a per unit basis because you're going to use more energy if you produce more output. It's just
correct.
Slightly. So
maybe I can chime in here. So for building side, we also use so-called per square meter or per square feet energy usage. So that's the profiling and energy benchmarking data going to be compared and matched. Yes, so definitely we work on the per unit. So we are able to compare data with benchmarking, also the cross United States data. Yeah. And because you mentioned is really the manufacturing device, right? So later on, per unit energy usage also can be compared, and we can predict, compare. And we noticed some abnormal operation. We can provide, alarm and remind the engineer and take a look into, right, all the details. Yeah, definitely. We need to put the platform awareness, the benchmark data, not only for building, but also for operation process and machines. Yeah.
Thank you.
Yep. Thank you.
If I could ask one other question, this is Ali.
Sure, Ali. Yeah.
Early the data you showed about energy administration was quite interesting.
Yeah.
Thinking when we look at commercial buildings, the metrics, how many people are there per unit feet and things like this. But of course, manufacturing depends on the tools, and manufacturing chemicals versus, pharma or metals will be very different. Are there any data per manufacturing sector saying that, on a machining operations, the energy per square feet or whatever per unit, are there things available?
Yes, they are. Yes, they are. If you look into energy information administration, they do have different manufacturing facility category for different process. So they do have clear data from EIA. All those data are actually from survey data. It's not a simulation result. Yes. So that's our second energy benchmarking. The job is actually to dig into for different category of manufacturer. Then we have the profile, like I mentioned, right? It's per square meter or per units or stuff like that. So for sure, it's not owning overall total entire building or entire facility, but break down category data. Yeah.
I see. And I guess going back to Daryl's question, so they have that data depending on the capacity, how much utilization, because, if you have the machines, you use it 50% of the time versus 80% of the time. Again, things changes. So the energy administration data has certain capacity factors.
That one, I guess, would not available. So it's more like a averaging, right, across United States, right?
I see.
So they're looking at the big data per units, per square meter, stuff like that. Yeah. So for our project, I guess a lot of new stuff like 3D printers, right? So we may not have data at all. So that's a chime in your group, right? Or the expertise in the manufacturing, so we can work together, make this profile, predict, right, later on. Yeah. Thank you, Ellie.
I have sort of an open-ended question. So in talking with people from 912, they seem to think that these energy costs are likely driven by events that are rare, so spikes in consumption. Can you give us some insights about how the AI model will be useful to treat with these rare event data?
So are you talking about the actual operation phase or the building behavior itself?
Either of those. So,
Okay.
in general, if you have data sets that that have rare events that lead to the energy costs being high. You talked about one of the drawbacks of the ML models are the amount of data you need to train them.
Mm-hmm.
So how do we think about, given that by design the data is less because they are rare events, how do we train a neural network or support it?
Yeah, I guess the fluctuation is really caused by for building. I'm just talking about building scope, right? For building itself, mainly caused by the weather disturbance, right? So you have solar irradiation, you have humid condition or higher temperature, stuff like that. Then for building itself, very critical, the materials fixed there, so we have relatively stable values for the properties. So the model will learn for those disturbance, right? And for the because of the R and C or some other design parameters defined. So this system is kind of just a changing dynamic according to the outdoor changing, disturbance changing. But once we think about the manufacturing facility, there are additional big thing come in rather than only outdoor condition, but the internal heat gain coming out, right? So for example, machine continues reject heat into the space. So it's different from our office building, right? Because each person is like a light bulb, also gives the heat, and it's easy to handle and to estimate. So by using metabolic rate, but for the device, we really have to have clue the energy, the heat rejection or stuff like that. But that is also as an input into the model. I guess we need to have all of those kind of later on ask the machine learning the model to learn for different type of the model, different type of devices, and different type of the manufacturing facility to learn this internal load, right? Because I guess prediction for weather we can make it easily because we have a history data. Then I guess the AI model can easily build the correlationship. But for this the machine and device, it also needs the AI model to learn. Then they put together. Yeah, I would say both disturbance from weather, also the operation, the device itself. Yeah.
Is this this is Rajacharya from Indiana. I think maybe the last question included demand-driven energy, because the bursty signals usually come in the power industry simply because of the nature of the usage, the load. Am I correct?
Correct. I totally agree with you, because for building side, right, we serve for people, right? So for people, so all the controls, so we call the demand control, demand ventilation control, how many people in these rooms, and we serve this many people, rather than nobody in here, we still serve. So I guess the same situation in the manufacturing facility. Do we run this facility, this device at all at this moment? So we need to have clear scheduling or learn the schedule. So this is the operation procedure has to be also incorporated into this model, this energy usage model. Definitely demand, right? Demand response, right? Really response those. Yeah.
So yeah, this is Pratik again. Just more of an open-ended question, perhaps a discussion to you and everyone else. What has been, in your experience, the missing or the noisy data that you have observed? So in general, is the data set clean, easy to analyze? What have been some of the pain points in analysis that you have faced that you can share, that can perhaps help the rest of us, and maybe you or others can chime in into some of the other characteristics of our nuances of the data set? That would be very wonderful. Thank you.
Yeah. Very good question, because after training, we noticed it's not a fixed, it's not always converged sometimes, right? Because we notice the weather in disturbance is actually it's very hard to get the converge sometimes. So gradually we figure out we can break down the learning according to the season. So we can have a sub-learning kind of models. So we have kind of rather than one simple overall learning, but subcategories and learning. So also self-learn, those kind of things involved into it. Yeah, so the noisy also, especially the people behavior. I mean, when we talk about building the self, the people behavior is very important. If you often open the doors, then you have a lot of load introduced into the space. So that's also is noisy sometimes. So we need but for this facility, I don't think it's involved too much of people behavior or those kind of things. As long as machine can be learned well, I guess the noise would not that big.
I bring this up because I think in general, a lot of these IoT sensors are pretty flaky, and there can be a very high risk of missing data, which I think we have also observed in simple analysis of this data set. And I think going back to even that CNC machine temperature graph, right, just somehow it doesn't feel right to me that even a CNC machine would go up and down in temperature that much every few seconds. So I'm wondering if there's in addition to the physical based modeling, we will need to come up with or use some techniques for denoising the data, or at least finding out which values are actually valid and correct.
Yeah, exactly. That's also somehow we just discussed, right? So the common filter or some other method, we can put in this uncertainty of the measurement, the sensor into the model. So I guess for our prototyping facility, we can install more IoT sensor, because the sensor, IoT sensor is so cheap, right? We can install more, so our estimation for the critical parameters could be more very well validated, right? Then later on, we can try to reduce the number of the sensors for the overall application. But for the initial one, definitely we need more data and need a more strong model to include all those uncertainty from both model side and also the measurement side. Yeah.
Yeah, I think those seem like great ideas. Thank you.
Mm-hmm. Yeah, thank you.
Well, Ming, looks like there are no more questions. Thank you very much for a very informative presentation and also excellent pointers for how to approach this type of research. We had some PhD students from Notre Dame that were listening in, and I'm sure they have learned a few things, at least, the starting points for the data we work with. So thank you very much for this presentation, and thanks for everyone who attended. The recording of this presentation will be available on YouTube, and we'll send everyone a link so that you can send it to colleagues who couldn't be here. So again, thanks a lot.
Will we also have access to the presentation that was shown?
Yeah, I can provide the PDF. Yep,
Great.
no problem.
Thank you.
Yep. Okay, thank you. Bye-bye.
Thanks a lot, everyone. Goodbye.
Thank you.
Thank you.
Mm-hmm.